This one? Okay. All right. So we're gonna dig in now, talk a little bit about cameras. And the objective of this is really to not get to the detail of building your own camera system, but to provide you with some of the vocabulary and information that you should know as you're starting to learn about coastal imaging. And one of the main points of this lecture is to help you with camera choice, which depends on your objectives, the budget that you have, whether $100 or several tens of thousands of dollars or even more, and your level of technical expertise. So you can get in and build your own system and do all the wiring yourself, buy all the components, or you can use your smartphone like we do with Coast now. So there's a range of entry points into coastal imaging. Okay, so we're going to go through a number of different camera topics and the related vocabulary. I'm going to talk about the camera bus, the sensor type, how a shutter works. We're going to talk about chips and chip size, which is really important as you're designing your coastal imaging station. We'll talk a little bit about depth of field and focus. The worst thing that can happen is that you don't focus your camera right, and then you're stuck with that, say, for the next several years. We'll talk a bit about resolution and choices between color images and grayscale and why you might want to choose one or the other. And finally, we'll talk a little bit about camera triggering, which really comes into play when you have a multi-camera system like an Argus style system. So the take-home points of this lecture are that your camera choices and settings affect the quality of your results. So depending on where you start off, depends on what kind of data you're going to get out. And different data collection scenarios require different types of cameras. So whether you're working in a really remote site where there's no cell phone service and you can only get there once every 6 months, is going to be a very different choice than if you're putting a camera on top of a hotel where you have access to internet and power. So when you're starting to think about developing your coastal imaging station, you want to start to think about what are your objectives for this data set that you're going to produce. As I mentioned, we're interested in a range of temporal scales when we're doing coastal imaging. So are you doing something where you're really interested on the minute time scale and setting up an action cam like a GoPro is going to be the solution for you? Or do you want to do some coastal monitoring for decades like has been going on here at the FRF? You're going to think about a very different approach depending on how long you want to have out your system. Another consideration is your power source. Do you have access to shore power? Are you going to be using a battery, or do you have a solar power system? That's going to make a big difference in what kind of camera and what kind of computer you're going to choose. How accessible is the camera? Are you putting this out somewhere where you can easily go access it every day or every month? Is it going to be on top of a tower or a mast that you might have trouble getting to? Or is your camera going to be located remotely on the other side of the world where if something breaks, you're not going to be able to get to it for 6 months or a year? And then you want to think a little bit about the phenomena of interest. Do you want to study waves and currents, which are changing on a second-by-second basis? Or are you studying morphology, which might be a little bit more static relative to the waves and currents moving over it? And then finally, think about your data link and storage. How fast of an internet connection do you have? Are you using cellular data or Wi-Fi? Are you going to be limited to just using an SD card on a camera, or do you have capacity to use a hard drive that you'll be swapping in and out? So all of these things can play into the choices that you're going to make for your imaging system. So just digging into some of the simplest parts of the camera that Kate already alluded to. If you have something like a GoPro, you probably have an SD card where you're storing your data. You have an image sensor. That's the image plane that Kate was talking about in the last lecture. Your camera has an aperture, so allowing light into your lens or into your chip, your sensor, and then a lens, which, as Kate mentioned, can cause some distortion. So those are some of the things that you're going to be thinking about on the inside of your camera when you pick one up. And then kind of the next level of camera would be one that's connected to a computer. This gives you more opportunities to make different choices about how your collection scheme might work. And that's going to be connected through a digital interface called a bus. So one of the first things that I'm going to talk about here is the bus. And I have to tell you this story that my first Argus workshop when I started graduate school, it was one of the first lectures at the workshop, and it was all about the camera bus. And I thought, well, what the heck is a camera bus? So this is the picture I had in my mind. I didn't know that it was the digital interface between the camera and the processing unit. And so there's a number of considerations when you're thinking about a camera bus. And you notice throughout all of these slides, I put references to websites where you can find this information yourself if you want to go in and read a little bit more than I have on the slides. So one of the first considerations with the bus is what's the throughput. So how fast can you and how much data can you send through your bus? This is going to depend mostly it's going to depend on the camera and the sensor that you choose. So larger volume of data and faster data collections require a bus that can put those data through to the computer faster. There's a range of price points for a camera bus. And so thinking about the cost of a bus is going to probably be an important part of your camera choice if you're building a more complicated system. Another thing to consider is cable length. So some cables can be hundreds of meters long. So if you have a camera on top of a tower high up, but you want to have your computer down on the ground where you can easily access it, you're going to think about the camera length versus having the computer located right next to your camera. Another thing to consider is a standardized interface. Some interfaces allow you to plug in different types of cameras. Perhaps you want to switch between an infrared camera and an optical camera. Some interfaces are going to let you do that with ease, and sometimes it's going to be more complicated. So that's something else you want to think about. Another thing to consider with the bus is some buses actually power the camera themselves. So this would be like a power over Ethernet sort of a cable. And so in some cases, that might be really convenient. In other cases, it's actually requires more power than if you powered it separately. So that's just something to consider. If you are, say, at a site where you had solar power, you might be very concerned about how much power you were using. Another thing to consider is how much CPU you're going to use, transferring those data back and forth, and whether your computer can handle that. And then finally, especially with a multi-camera system, you're going to be thinking about how you're going to trigger that system, and some of that can happen over the bus. So there's a number of different sort of types of buses, and these are just examples of some of the names of them and some of the trade-offs that you can have. So, do you really want to collect large amounts of data fast? You might make a different choice than if you just have a really low resolution camera and you're going to be sampling slowly. This is the same kind of information just put into a bar chart to help you make choices about what kind of a bus you might want to choose. Or if you're looking at a commercial system that's already put together, this information might help you decipher some of the manufacturer's information. Okay, moving now on to some other considerations when you're buying a camera. You might want to think about the sensor type. So sensor type controls the quality of the camera, or the quality of the image. And our little, okay, so up in the upper corner, you can see a little bit what Kate was alluding to when she talked about the description of photogrammetry. So the sensor takes our light and puts that into an electrical signal that we can then save. And that's basically how we produce our digital images. So there are two types of sensors that are typically available in cameras that we use for coastal imaging. One is a charge coupled device, or we usually call it a CCD camera. They tend to have a global shutter, and I'll talk in a minute about what a global shutter actually is. They tend to be lower noise and have a slower readout, so you can't sample as fast as you can with the alternative, and they tend to be a little bit more expensive. This would be like a machine vision camera, so at a, could be a price point of a couple $1,000s. And then the alternative would be the CMOS sensor, complementary metal oxide semiconductor. These tend to have a rolling shutter, and we'll talk a little bit about what the consequences of choosing a rolling shutter mean for coastal imaging in a second. In the past, CMOS sensors tended to be higher noise than CCD sensors. That's not the case as much anymore. The engineering's a little bit better, so some of those noise problems have been resolved. They tend to have a faster readout, so if you want to sample faster, this is a way to do it. They tend to take lower power, and they tend to be less expensive. So CMOS sensor is what you might find in a less expensive action camera, so maybe at a price point of a few $100s. Okay, digging into the next consideration is the shutter. So I mentioned this with the type of imaging sensor. You can either have a global shutter or a rolling shutter. And here are some of the considerations when you have a rolling shutter. There's a few effects that can happen. One is some spatial aliasing, and this is a picture that John Stanley put together, and he had a great sense of humor. And so a well-rested propeller or a very, very tired propeller, and that's because the image is being aliased by the rolling shutter. Another effect is a jello effect, and so say if you're taking an image with a rolling shutter on a drone, you might notice this wiggle in the sensor, and this is from a paper that describes some of those effects on a UAS. And so you can see what that jello effect looks like. So some of the differences, the technical differences between the rolling shutter and the global shutter are the way that they sample the sample light. So in the rolling shutter, you have your chip, and it is exposing the image row by row on the chip. So here you can see where fully exposed row, and then the exposure is underway to the point where it's being initiated. So that's how you end up with that wobble in the image, because you're sampling through time, and if your camera is moving, you'll get that jello effect. Alternatively, you have a global shutter where the sensor is closed off, then open, exposed to light, all at the same time. So you get the full picture all at once, and then closed again. This tends to be the most accurate representation in motion. And so when we're thinking about wanting to image waves, this is an important consideration as to whether you're going to use a rolling shutter or a global shutter. And like I mentioned, this is typical in a machine vision camera. Yes?
What do you mean by noise?
Pardon me?
Noise. What do you mean by noise?
Like signal to noise in the light. So how much sort of static are you getting in your image? Okay, another consideration when you're thinking about the sensor in your camera is the chip size. So here is just a number of different sort of standard sizes that you might find on a coastal imaging system. An important point about chip size is that the chip size that comes from that you see in the standard information from the manufacturer is not actually probably the chip size that we need to consider when we're building a coastal imaging station. And so you need to make that calculation for yourself if you want to do something like calculate your fields of view. And so let's see, what else? One important thing about considering your chip size is actually knowing what the true chip size is when you're going to purchase your lens, purchasing your lens separately, because if you make a mistake between the lens you purchase and the sensor size, you can actually end up with vignetting, and I'll show you an example of vignetting in a second. So this is an example of vignetting, and it's a reduction of brightness around the edge of the image, or you can actually accidentally block off part of the image if you have the wrong lens size. Sometimes we want vignetting, so in this nice romantic wedding picture, maybe the photographer was being artistic and we want that look, Also, stock GoPros have vignetting built into their firmware. So that's just something to consider if you're working with a GoPro, that may actually have probably has vignetting built in. And then we also find vignetting in infrared imagery, and that can be due to temperature differences on the chip. So that's just something you might see as you're working with imagery. So digging in a little bit to determining the chip size, and this comes into play when you're planning your station and you're thinking about what's the footprint of my image on the ground and what's the field of view. So the first thing to do is to determine the physical size of the pixel on the chip, and you can find this. I'll show you an example in a minute. You can find this in the if you dig into the manufacturer information. And then the second thing that you need to do is to multiply that pixel size by the number of pixels on your CCD or CMOS chip. From that information, along with the focal length of your lens, you can calculate the horizontal fields of view. So the important pieces of information that you need are the chip size in millimeters and the focal length of your lens in millimeters to get your horizontal fields of view. So I'm going to step through this example. This is with a FLIR Blackfly. So that's a typical coastal imaging camera. It's used in many Argus style systems. And we're going to dig in a little bit more to this in our station design toolbox lesson, which we're either going to do after this or possibly tomorrow, depending on how we're doing on time. So the first piece of information, and this is right from the manufacturer website. You can find this for any camera if you start searching around the manufacturer website, the resolution of the camera. And so that's telling you how many pixels are on that chip. So 2448 by 2048 is a pretty standard size for a camera, for a 5 megapixel camera. Here is the pixel size, and we can take that information and multiply that out and actually calculate the size of the pixel or of the chip in millimeters for our horizontal fields of view calculation. Notice that the information from that if you just look at the general information about the camera, it'll tell you that it's a 2/3 inch lens or a 2/3 inch chip, and that's not actually the size of the chip. So as you go to put your information in a station design toolbox in a later step, you'll actually want to make that calculation yourself. Another thing to consider is that the smaller the size of the chip, the shorter the focal length that's required to get the same field of view. And so here's just an example here of two different focal lengths, or two different chip sizes, and the focal lengths that would go with those to achieve the same field of view. Another thing to consider when you're making these choices about focal length, chips, and lenses is that a shorter focal length will result in larger distortion. And we'll talk a lot more about distortion later, but that's something to keep in mind, that bending or fisheye look of the image that you might see in a GoPro can be controlled by your choice of lens and focal length and chip size. Another thing that you want to consider with chip size is the sensor sensitivity. So if you have a larger chip size, you'll have a lower signal or a higher signal to noise ratio. And so when you think about photographers, maybe professional photographer uses a very large chip size to achieve really crisp, clear images. So along with that, smaller pixels gather less light, so maybe not as clear of an image. More light requires a smaller f-stop, and I'll show more about f-stop in a minute. Also consider a larger iris can result in more distortion, and a larger iris results in a smaller depth of field. And so these are just a few things, some sort of basic photography vocabulary that you want to think about. Again, the aperture size controls the depth of field and focus. So you can see for an f-stop of 16, you have a really wide depth of field, whereas for a lower f-stop, you have a much narrow depth of field. So lots of your images out of focus, and some of the images very in focus. Here's an example of two different images of this bunny rabbit, and they're taken with a shallow depth of field and a deep depth of field. Typically, in coastal imaging applications, we're trying to image information that's up close to the camera, maybe the beach, but we also want information in focus far offshore, and so we would typically want to use a wider depth of field. This is just a little bit about best practice if you're focusing your camera. Start focusing with the iris wide open to get the best results of focus at a distance, and then close that iris down to get the depth of field that you want to, and then check that the focus of the image. If you can actually do this in the field while you're installing the camera, that's ideal. Otherwise, taking it outside of your office or lab to do that focusing is a really nice thing to do, so you don't make a mistake. Like I said, I've learned from experience, if you don't get great focus, you can be stuck with that for a long time. So it's an important thing to spend a lot of time on. Another thing to consider is the resolution of your images. It's amazing to get wonderful high resolution imagery, but then you have to deal with that volume of data for as long as you have that camera out. So typically, cameras are referred to in terms of megapixels, and that correlates to the number of pixels on the sensor. So here are just a few examples of typical sensor sizes used for coastal imaging. Higher resolution cameras and image sensors require higher resolution lenses. So you want to be really careful if you're buying a nice new HD camera that you buy a lens of equivalent quality. The challenge there is that if you put a lower resolution lens on a really nice system, you might end up with a fuzzy image. Also, higher resolution or higher quality lenses tend to be much more expensive. So as you're considering the cost of your station, you also want to consider the cost of that lens that you're going to end up purchasing to produce a nice image. Another one to think about is whether you want color or grayscale. Color can be great and valuable for many reasons, but there are also reasons why we might want to choose a grayscale image. So there's a trade-off between the image resolution, the sensitivity of the image, and the volume of data that you're going to collect. For example, because of the way that the sensors are built, a grayscale image is receiving 3 times more light than a color image, which is where the light is being filtered. You can see in this little drawing down here, each box represents a pixel, and each pixel has a color filter on it. So some of that, a certain wavelength is coming in and being received by the sensor, and then the rest of it's being filtered out. Whereas with grayscale, it's allowing all wavelengths of light to come in. When we work with a color image, we're actually doing some interpolation that I'll talk about in the next slide. So that's another consideration, is you're actually sampling at lower resolution. And then your data volume, you're collecting 3 times as much data once you do that interpolation when you have an RGB camera. So a little bit about the way a color image works. You have your chip, and you have different color sensors or filters on top of each pixel. So as you're sampling, you're actually sampling one color at each pixel and then interpolating the other colors at that location. That's called a Bayer pattern. This RGB pattern is named Bayer after the engineer who developed this approach of imaging. And this is just an example of, if you actually zoomed in on a CCD chip, what that RGB grid would look like. Moving on to some other things that you might consider as you're thinking about the trade-offs for your system is, how are you going to acquire the imagery? So if you're working with a camera and a computer, you have to have some software that's going to help you acquire that imagery. There are a number of different choices, and as with all of these choices, it depends on your technical expertise and your time available, things like that. One obvious choice for Argus-style coastal imaging is to choose HOT-M. That's the image acquisition software that was built out of Oregon State, and that's now available on our Coastal Imaging Research Network repository. So you can go grab that, help develop it if you're interested in that. There's also a number of commercial systems and commercial software available, and I've just listed a few here that I've worked with in the past, but there's many, many different types. I'll mention Argus Eyes if you were is a newly developed software that is a sort of a commercial version of the OSU Argus system. And then there's a number of different scripting languages where you can acquire images. MATLAB and Python are some examples of those. So lots of different choices depending on what you're looking for, what your needs are. And then a final consideration is if you're working with a multi-camera system and you want to do work like image waves, so like to run CBATHY, or perhaps you're interested in doing stereo reconstructions of the water surface. In those cases, you're going to want to have really highly synchronized cameras, and you can do that with an external trigger. This is just an example from the FLIR Blackfly, again, of the GPIO cable or GPIO input where you can actually do that triggering. And there's also a number of other ways to do it internally through software. And depending on your choice of bus, you might be able to actually do the triggering through the bus. There's a number of different possible commercial choices for cameras. These are just some examples of different ones you might consider, going with something like a standard off-the-shelf security system is one option if you're not interested in digging in, but that will come probably with trade-offs about the rolling shutter and the quality of the lens and sensor. There's some things like the CamDo GoPro system. It's solar powered and it uses a GoPro. So maybe if you're putting something up remotely, it connects to the internet. That might be an approach for you, or a modified GoPro that takes out some of that hardware and puts a higher quality lens on. That's another option. There's also things like machine vision cameras. I've talked about the Blackfly a lot, or choosing an infrared camera. If your imaging approach requires infrared imagery or imaging at night, that is another option. There's a number of streamlined hardware solutions that folks in the CIRN world tend to use. Of course, we have CoSnap, and our CoSnap friends just left to do their part of the work or the boot camp separately today, but that's definitely a low cost, citizen science approach. Kind of taking it the next step up would be moving to trail cameras. You can purchase off-the-shelf systems now where you can download data from the web that those images collect. That's another option if you're kind of moving up. Again, that's going to come with the trade-off of probably lower quality lenses and sensors, but the trade-off is it's very streamlined and easy to put up a trail cam. And then kind of going to the highest level of quality would be an Argus style station. It's going to provide scientific quality cameras. It's going to be the most expensive approach and may require some technical expertise to build yourself, or purchasing a commercial system and then working with a commercial company to help manage it if it's new to you. So in summary, we covered a whole bunch of different vocabulary related to cameras and photography. The choices that you make about the camera you use for your coastal imaging system really depends on what you want to get out of it. There's from using your cell phone all the way up to a very expensive coastal imaging system, and depending on the quality of, say, your infrared camera, you could go up to the hundreds of thousands of dollars very quickly if you chose to. And it all just sort of depends on what you need. There's no one right answer. There's no one best camera. It all depends on your situation. That, I think, is it for me. Yes. should ask, does anyone have any questions on that? Alex?
With the IR cameras, is that typically like adding a fourth pixel to your RGB? So would you have like a quarter as many, or is that like another layer? Or?
So let's see. I'm trying to think. So if you're working in the near infrared, you can actually, so for example, the point gray cameras can sample in the near IR. You just have to take off you would get a grayscale camera and you would take off the filter that's actually filtering that data out. So you could do it that way. And then if you're at a real infrared camera is a completely different type of sensor than the optical sensor. Mark?
Yeah, could you talk a little bit about camera housings and then like I'm curious, like if you switch camera housings, you have to do new intrinsic calibrations, and then like with all type of lenses and having the right resolution for the lenses, like you're going through another piece of glass or plastic or whatever for housing. How does that play in? Does it matter? Can you do any kind of housing and does it change anything?
Yeah, you should account for the glass in the housing, and there are different qualities and types of glass you can buy depending on your situation. So, if you're high up on a hotel, you're not getting, say, sandblasted. You might choose a different quality housing and glass than you would if your images or your camera's going to be down in a dune where it's going to be hit by sand all the time. And so, yes, you would definitely want to account for that in your calibration. In practice, do we always? Maybe not.
And it's because there's no curvature on that lens, it's not as sensitive to everything else.
That is probably true, although there would still be imperfections. Any thoughts on that?
Best practice would be to do your intrinsics with the camera in the case that we're doing.
It also gets even more complicated now that our cameras have gotten smarter, that there is already algorithms you don't even know that's happening inside the camera that's undistorting things. So we always try to turn, sometimes we like to turn that off on certain UAS just to make sure we know exactly what's happening. So that is one thing to think about for camera selection. These newer, more expensive UAS and cameras have auto stabilization. And we found that really, when you're trying to stabilize the waves, it doesn't really help. So we try to turn all of that off. But, so a lot of times, and it's kind of a judgment call what you're actually looking for. Like, you can get away with not even doing distortion on some of these already nicely undistorted images, but it's a trade-off. So, but yeah.
Greg?
Yeah, can you give a sense of the different camera that you have at price range? What do you expect with different type of uses that you had at the beginning? And so if you take the medium range, what do you expect in general, like in terms of the level of errors that you can get, so you can get like beta scale waves or centimeter scale waves?
Yes.
What can we expect?
Yep. Thank you. And so it actually has it on the bottom of my slide here. So for the kind of lowest level, say from your coast snap station, you can get information like the position of the shoreline or the location of the sandbar in a single snapshot, and it is more of a qualitative estimate. Moving to a trail camera system, that's going to have the rolling shutter, and so that's where you would be hesitant imaging waves. It will give you most likely a good shoreline position or sandbar position using a time exposure image, so where you're averaging over many images. And then moving to that more research grade system, that's where you're going to be using the global shutter and the higher quality optics, so the higher quality CCD and lens. And there we'd be comfortable imaging waves as well as doing the other things like imaging sandbars and shorelines You're going to be able to image currents in that case, so making time-dependent sampling, that, and we'll talk more about that later. So
You're saying that if you want to do things on the order of minutes to seconds, you need to have the side of things, where you can do things on hours or things, you want the workflows and the program.
yeah, that's an excellent way of thinking about it.
I would say as you go from Argus to CoSnap, you have less control. So like Argus, you can run it whenever you want, the frame rate, whatever you want, trail cameras, you're set by the parameters by the manufacturer. And then CoSnap, it's just whenever someone takes a picture.
So I've found it's very quickly, you have to get to the research grade if you want to do, scientific work.
In terms of the imagery for the trail cameras and the Argus, is it just the distance that you set the camera? They can both see change. It's far.
I'm going to actually hand that to Brittany because she has the most experience.
I would say we're investigating the use of the trail cameras. I would confidently say they can do shoreline and conditions the best. So like I said earlier, we are limited to certain frame rates and and durations. And so we can't replicate a regular CDAP collect. Also, the resolution isn't probably as amazing, and there's a rolling shutter. So I can comfortably say like shoreline bar position with the trail cameras, but not the imagery.
To clarify, by bar position, Brittany means you can do a quasi Timex. It's not sampled as frequently or for as long as the traditional Argus Timex, and you can see where waves are breaking in that Timex, which is a proxy for the sample resolution, but you are not getting bathymetric depth.
Any other questions? Mark?
With the rolling shutter, say you just up the frame rate to really high, like how slow is the roll, I guess? Is it fraction of a second or is it?
Yeah, I actually don't know the answer. We can find that out.
At least with the trail cameras, we found that they have a very slow rolling shutter. Just where we were trying to do our intrinsic calibration, holding the board. Like if someone was holding it, like we would see like the board move halfway, like it didn't, so it was that sensitive to that. So, but in terms of like using GoPros, we've had really good success using those. So I think it's the quality of the camera as well.
I don't know if that's like a parameter that people advertise. I'd say, like it should, like Brittany said, it should be a problem on the GoPros, but we've been able to use GoPros on UAVs to great CBAC data collects. So they're really shuttered. I mean, as long as it's not super high waves, the UAV is not like.
That rolls the whole frame at once. The rolling shutter, not like it's like full frame almost. Does that make sense? Or is it like row by row? Like row by row.
The shutter like rolls open and it's going through the close.
So like bag kind of.
Usually, I think top to bottom.
Oh.
With the global, it's like open.
Yes.
I was gonna ask rolling vertical shutter, what kind of difference is there in power and stuff?
Oh, I don't know that. I don't know the answer to that.
Yeah, sure. Bigger it's the camera. Just across the board, I'm guessing, like, is it much higher for the bigger global?
The global shutter, that would be my guess, but I
It
don't.
costs a lot more.
All right. Let's see.
That's a quick question.
Oh,
So
yeah.
like sort of relating CoSnap to something more tech or high tech. Do you know of anyone that's used like cell phone cameras to do trail camera Argus style collection? I don't know if that's
It's one of our discussion topics, like Thursday, actually, just, you know.
There.
Yeah, I actually saw a presentation at Coastal Sediments a couple weeks ago where someone had done that. They had mounted a cell phone camera in like a watertight type case and mounted it on like a tree at a cliff in Puerto Rico and gotten some trail camera type level data by having a permanent cell phone camera that they could go and download on a regular basis.
And what most quality cases then?
Drones, well, I would say it would depend on the drone, and the sort of quality of probably the price point of the drone would tell you a lot. But I would say it would fall in the kind of trail cam range, unless you can buy a really expensive drone and put a really expensive camera on it, and the answer would be different.
You can get a lot of the Argus products, but the drones typically with the default cameras have the rolling shutter, and so there may be higher errors in what you're doing with the Argus products. Like you can do CBATI from a drone. Trade-offs.